Hello, and welcome to Innovations in Infection Control for 2021. My name is Dr. Bridget Sterling, and today we're going to cover a number of different information packets within this module. This module is designed to present up-to-date information on infection control in order to improve workplace knowledge and make your practice safer. The first place that we want to start when we're looking at any kind of a pandemic or epidemic situation is to know who your enemy is. In this case, our enemy is a virus. And even though we might be thinking, we don't want to talk about or think about viruses anymore, even though we might be tired of thinking about this pandemic, the virus is not tired. In fact, the virus is just warming up. The second severe acute respiratory syndrome coronavirus, or SARS-CoV-2, is small. It's actually about 1/100th the size of every one of your human cells. Coronaviruses have protein spikes that sit on the outer surface of their cells and allow the virus to attach to protein receptors in your human cells. Then the virus inserts its genetic material into your cell. It gains access inside the cell's membrane by making contact with human enzymes on the cell surface. Once it's inside the cell, the virus's genetic material uses the cell's own resources to replicate. So these cells are kind of lazy. They're not living, and they need you in order to replicate. So after the virus enters via your nose or eyes or mouth, it has to find a host cell to attach to. Then it has to inject its genetic material, or RNA, into it. Then the infected cell uses the SARS-CoV-2 RNA to make replicas of the viral genome. Each infected cell can release millions of copies of the virus before the cell finally breaks down and becomes inactivated. Let's look at some facts about the virus. We know that SARS-CoV-2 moved from Wuhan, China in late 2019 to virtually every major population on Earth within 4 months. People are most infectious on the day that symptoms begin. So if someone begins to have fever or cough or tiredness or aches and pains, then that's probably the day that they are most infectious. About 17% of people are completely asymptomatic, meaning that they never have any symptoms and they probably don't even know they're infected. Unfortunately, some people do die of SARS-CoV-2, and it varies greatly between different populations as to the number of people who have tested positive or who are post-death tested positive for SARS-CoV-2. And that's dependent on a number of things. Obviously, if you're not testing, you're not going to have a number of people who didn't die or didn't access care. You're not going to pick up those asymptomatic people. So you're going to have, if you're not testing, you're going to appear to have a lower case fatality. But for example, with countries that are testing a lot, they're going to see a lot of people who have the virus who don't die or don't even get sick. There's lots of important factors when we think about case fatality, so the number of people that die. In Italy, about 20% of people in their 80s or above died if they contracted COVID, while only about 1% of people in their 50s did. So age is important. And we have to also consider underlying conditions, which are also associated with age. So for example, in China, about 10.5% of people with cardiovascular disease died if they contracted COVID, while less than 1% of people with no underlying health conditions died. So that's important also. So now we have age and we have underlying health conditions that determine people's risk of dying. But why has SARS-CoV-2 infected so many people worldwide? Well, the reason is because it is highly transmissible. The way that we look at transmissibility as epidemiologists is in the reproductive number, and we may consider the RE, which we consider the effective reproductive number, which looks at how diseases spread, and this number changes over time because it's depending on susceptibility. So as you do things like vaccinate people, or there's more people with past infection in the population, or human behavior changes, then the number changes too. Our goal is to get the RE down below 1. So let's look at something else though. So that's the RE, which is the effective reproductive number, which changes because it's based on what is happening in the population. But we have another number which is just called the reproduction rate, or R0. And this is the number of people who are infected, who become infected when they're exposed to one person. So for every one person who's infected, the RO is the number of people who subsequently get infected by them. So you can imagine if the RO is 1, then you would just continue on. One person infects one person infects one person, and you just have a stable number of people in the population. As the number rises above 1, it goes exponentially higher. So if one person infects 2 people, then those 2 people go on to infect 2 further people, and you can imagine with a very, very short period of time, you would have a lot of people infected. The novel coronavirus's RO is between 2 and 4. So for comparison, H1N1 has an RO of 1.5, so it continues to grow as an epidemic when it gets started. And measles, which is incredibly highly infectious, has an RO around 18. So that means that if you do nothing, if you don't intervene, you don't vaccinate, you don't have a number of people in the population changing their behavior, that for every one person that gets measles, 18 people will get it from them. So you can imagine how explosive measles is in an epidemic. But yet, what are we talking about here when we consider SARS-CoV-2? Because we do have an RO of between 2 and 4, but we can get that down. We can change our behavior. And so our RE, our effective reproductive number, could lower down to, say, 1.5. That'd be amazing, right? Our behavior changes and we're able to reduce it to as little as 1.5. And that's great, except the numbers don't help us. So if we have an RE of 1.5 and we had 1,000 people who are infected in a population, those 1,000 people would infect 1.5, right? 1,500 people, who would then in turn infect 2,250 people, who would then infect 3,370. You get what I'm saying. So if you start with this small number, it will just grow and grow and grow until there's exponential growth. So we don't want to see that. And that's the reason why we've seen so much growth of this particular virus. So even if our behavior changes, we still see problematic growth in the population. And in this case, as we started out with those 1,000 people who had reduced the RE down to 1.5 with COVID, we would still see in a population, a big population, around 11,400 people infected and potentially 200 deaths. So by 2 months, those 1,000 people would have infected enough people potentially to kill 200 people. So this is a problem. And even with fairly good behavior, not super restrictive behavior, we can have issues. So how do we calculate something like the reproductive number? So if you consider how many people there are in your population, and then the number of people that those people contact in a day, and then the rate of new cases that already exist in the population, that would give us the number of infections that we would expect to have. The other thing that's really important in understanding how diseases are going to spread, or the reproductive rate, is to think about how long a period of time people are not showing any symptoms but are in fact unwell. And that's a very dangerous position to be in. If you've got people that are in your society, the walking well, we call them, that are kind of going around they walking around and they seem to feel like they're well, but unfortunately they have the virus and they're able to transmit the virus, that period of time is important to know. And so is the period of time in which they are unwell and then interacting with the healthcare system and family members and all that kind of stuff. So that duration of time is important, and also the amount of time it takes for people to recover or, of course, to die. So those are really important things to know about any disease. And what we know in the case of SARS-CoV-2 is that clearly the reproductive rate was very high. And you can't argue with the fact that from the time that we even understood this was a problem, right, back in December, until this graphic was created in April, which is really less than 4 months, we can see that there was some confirmed cases in almost every country in the world. And that's very troubling. So we can, whatever we feel about transmissibility, we have to acknowledge the fact that, in fact, this is a highly transmissible disease, and it has been affecting a lot of people. So a lot of you have been hearing recently, I'm sure, about mutations. And so when in addressing the innovations that we're looking at in SARS-CoV-2, I did want to speak to how viruses mutate. So soon after SARS-CoV-2 was detected in China, researchers began analyzing viral samples and then freely sharing them and their genetic codes online. As the virus spread, it made copies with and between humans and animals, and of course, it picked up mutations. And this is very, very usual for viruses that are RNA viruses, like coronaviruses. So not long after the first SARS virus began circulating in humans, it developed several kinds of different mutations. And the first one it had, we called a deletion. And we were all hopeful, like, hey, maybe that deletion that is shown is going to slow the spread of the virus. And that was a real hope that we all had. But unfortunately, it didn't. And in fact, that initial mutation made the virus more transmissible. So this virus has been mutating since the beginning, but not as quickly as some other viruses. And so we were hopeful that either it would mutate into something that was less transmissible, or that it wouldn't mutate very fast. But sadly it has. And as the SARS-CoV-2 has mutated and made mistakes, it's moved from person to person. It's become better at sticking to the human host enzyme, and potentially it looks like it's increasing viral shedding, which is a concern. So it means that you're shedding more virus. So the average human with coronavirus will shed about 100 billion viral particles in the course of their illness. And unfortunately, it looks like some of these mutations are even increasing that. So what do we know about these mutations? You've heard probably that they're South African or that they're UK variants. We don't know where the mutation took place. It's really the consideration is where was it actually identified? Who found it? And so that's why the South Africa and the UK are being identified as places where these were first seen and described. So we have two very significant ones. There are other mutations that are circulating, but if we look at the B.1.7, it was identified in the UK in December of 2020, and it obviously led to some very severe travel restrictions and a widespread lockdown across the country. So the government reacted very quickly and was extremely concerned. And unfortunately, we have seen cases in the US and in Canada of that same mutation. And now that mutation, unfortunately, is representing about 70% of the new cases in some cities in the UK. And another variant of SARS-CoV-2, which is called the B.1.351, has emerged from South Africa. And cases that are attributed to this variant have actually now been detected outside of South Africa, so it's unsure where it came from originally, but it certainly now exists. Unfortunately, preliminary data show that the new variants are more transmissible, but thankfully do not likely cause more severe illness than the familiar forms of the coronavirus. So why are we so concerned about mutations and new variants of this disease? Well, and we're concerned because we don't know if changes made on the mutations will help this virus to evade detection by specific tests. Now, so far they have not. So it looks like the variants that we described already and that we know of are able to be picked up by our current diagnostic testing. There is a possibility that we will have decreased susceptibility to therapeutic agents like monoclonal antibodies, which are genetically modified antibodies. So there's been scientists that have been looking at naturally occurring antibodies and choosing the ones that are the most effective against the virus, and then cloning them, and then growing lots and lots and lots of them, and then helping people in treatment by then giving them these antibody cells that were made in the lab. But the concern is that the mutations may render some of that work less helpful. There's another concern, of course, that it could cause either a milder or a more severe disease in people. And as has happened, the concern is that it might also be able to be spread more quickly. So that is the concerns with the new variants. So one of the things I really want to highlight is that transmission of disease encourages mutations. So the more that a disease moves from one person to another, the more likely that mutations are to take place. So let's do all we can to reduce transmission. And how do we do that? We're going to be talking about that in this module later on, through physical distancing, through using PPE, from staying home when sick, from environmental controls, and of course vaccination, which we'll be talking about next. And we also need to monitor and track variants. So we need to do point of care testing. So people need to get tested if they're sick. And this will help to pick up asymptomatic people and super spreaders and lots of different people. And we also need to test specifically for different variants and adjust our vaccines if necessary as well. So that's a good segue into the next section, which is on vaccines. So in order to return to a more normal way of life and work, we'll need to reach vaccine herd immunity, which we'll describe later. Vaccines help people develop immunity to a virus or other germs. They introduce a less harmful part of the germ or something created to look or behave like it into a person's body. Vaccines encourage the body's immune system to develop antibodies and fight that particular germ and keep the person from getting sick. Later, if the person encounters that germ again, their immune system can recognize it and remember how to fight it off. So what do we know about the COVID-19 vaccine? Well, it's really important for people to recognize that safety is the top priority for governments. They're not interested in making you sick. And so really they've gone and done some amazing work at allowing vaccine developers to do several phases of the vaccine development at the same time. So no steps have been skipped, but they have been done simultaneously, and the permissions have been granted much quicker. So that's an important thing to remember. 2 doses are needed of any vaccine that we have so far, and that's because there are 2 different kinds of immunity, and in order to have long-lasting immunity, you need to boost your body's memory of that virus or antigen of any kind, so that your body will produce long-term antibodies. And so you will have a second shot 3 to 4 weeks after you have your first. And after COVID-19 vaccination, you may have some side effects, and this is completely normal. In fact, this is telling you that your body is building protection, as long as it's not something that interferes with your health or your life. And also, COVID-19 vaccines are one of many important tools to help us stop the pandemic, but they are not the only one. So we need to continue doing all the other things that we were doing before. But there are some challenges when we consider vaccination. In Canada alone, 38 million people are going to need to be vaccinated. So how do we do that? So rolling that out is going to be a little bit complicated, and it's going to require some coordination. There's also a lot of misinformation out there. And so we often talk about people having vaccine hesitancy. And what that is that when people have misinformation or lack of knowledge or some kind of anti-vax sentiment, then the population may become somewhat hesitant and fearful. And so we just really need to help people and come alongside them, encourage them, and educate people so that they have the information that they need to make good decisions and the best decision for them and their family. And of course, another challenge is that some of the vaccines that are coming out are mRNA vaccines, which are fairly new, although we have had some other vaccines that are mRNA vaccines, but they are for older people and not for younger people. So it is new that this is going to be given to younger people. So how do traditional vaccines work against viruses? Well, they give the immune system an altered form of the virus to trick your body into creating antibodies. So essentially what scientists have done is developed weakened or killed forms of the disease and injected into the body. And this has been happening since Edward Jenner back in the 1700s injected a little boy with cowpox virus and then later injected him with smallpox. And of course the cowpox protected him and everyone was thrilled. Of course there are major ethical issues with that. But nonetheless, it did demonstrate vaccination, and of course coming from the Latin word for cow, vacca. So vaccination is now what we do to prevent disease in people. So in the same way as Edward Jenner put the cowpox into that little boy, scientists make some kind of a weakened or killed form or altered form of the disease that's injected into the body. And then the body creates specific antibodies that will recognize and neutralize that particular virus. And then the actual virus comes along, and suddenly the antibodies are right there and prepared to attack it. And this is particularly true if the body has been exposed twice, at least twice, to the antigen. So anytime that you have a booster shot, you have one vaccine, and then sometime later you have another one, you're really helping your body to have good long-term memory. And that's our expectation for COVID-19 vaccines. Let's hope. So how do mRNA vaccines work against the virus? So we've said that they're different from traditional vaccines, so let's see how they work. They give the immune system genetic instructions to recognize the virus that's a little bit different, not actually giving them killed virus or weakened virus, but actually giving them a genetic code. So scientists synthesize the genetic sequence on the spike protein of the virus, and then the vaccine contains the instructions that the cell needs to make the spike protein itself. The synthetic RNA is then packaged into a fatty nanoparticle that delivers the instructions to a cell. So instead of actually having it sometimes we use a different virus or something else to deliver the vaccine or the vaccine sequence into a cell. In this case, the mRNA viruses that we have are using very, very tiny little nanoparticles of fat to actually deliver it. So once inside the cell's internal system reads the mRNA instructions and follows them to produce viral proteins. These are displayed on the surface of the cell to stimulate then an immune response. So your own cells are going to turn into little machines to create antibodies to COVID-19. Well, how effective are these vaccines? Of course, only time will tell because we don't know a lot about what the long-term effects are, for example. But we do have clinical trials and studies that have been done. So phase 1 for safety, and phase 2 for immune response, and phase 3 to see the effectiveness. And so that's what we've been seeing simultaneously a lot of the time with these vaccines. So we have Moderna, which is from the USA, and it's 95% effective in the clinical trials, right? That's what we found. And the mRNA vaccine, it has to be stored up to -20 for up to 6 months, or can be stored at -20 for up to 6 months. And it comes in 2 doses that are 28 days apart. And that is the most expensive vaccine we're going to talk about today at $33 US. Then we have the Pfizer and BioNTech from the USA and Germany, also 95% effective. It's also an mRNA vaccine. And it must be stored at -70 degrees. So you've probably heard a lot about this. It has to be kept very, very cold. And it can be given in 2 doses, 21 days apart. And that one costs about $20. You may also have heard about the AstraZeneca and Oxford vaccine from the UK and Sweden. It is, now in the clinical trials, they had 2 different arms of the trial, meaning that they did things differently in 2 different arms. And one of the arms was about 90% effective, and the other one was 60 some odd percent effective. And so altogether, when you added everybody up, it turned out to be about 70% effective. So it's a little bit less effective in that sense, but they seem to have worked out the dosing issue. But based on genetically modified zoonotic cold virus, in fact, it came from, I think, a chimpanzee. So the original virus that they're using to bring the spike protein to your cells is actually one that doesn't affect humans, but has been found in chimpanzees and has been genetically modified to not hurt you, and that virus will deliver the spike protein so that your body will start creating antibodies. So this is much better for logistics because this AstraZeneca and Oxford vaccine only needs to be stored between 2 and 10 degrees Celsius. It works effectively in different age groups, and it can be distributed much more easily and costs only about $4 and can be made in huge, vast numbers. So we're really hoping that developing countries might be able to use it as well. Yes, and so let's now move to Canada's vaccine. So Canada's vaccine, Medicago, is completely plant-based, which is fantastic. And this approach uses living plants as bioreactors to produce non-infective versions of the virus, which are called virus-like particles. And these virus-like particles present the antigens to the individual's immune system very efficiently. So this elicits a protective and long-lasting immune response. And they have done their phase 1 safety trials. They're in the midst of doing their phase 2 trials with about 30,000 people with different age groups and backgrounds, etc. It also requires 2 doses like all the other vaccines. And they're hoping that the efficacy results will be ready by spring of this year and will roll out with actual vaccines by the summer. And so Canada has reserved 80 million doses of that vaccine. And so hopefully by 2024, this vaccine will produce up to 1 billion doses per year. So we may need to continue to get vaccinated. And if so, we have a lovely plant-based vaccine made here in Canada that will be available to us. So who should get vaccines? Well, everyone eventually who wants one will be able to get one. If, of course, people have allergies to vaccine components, they won't be able to. There's some questions about pregnancy and about children, of course. We'll talk about that a little later. There hopefully will be a pediatric vaccine by the end of 2021. So, however, in the meantime, right now supplies are very limited. So there are priority groups that governments are considering. And so they're looking at whatever efforts could be made to decrease death and serious disease as much as possible. They're looking at preserving the functioning of society, so people who are in key positions in order for society to function will be considered. And also at reducing the extra burden that COVID-19 is having on people already facing disparities. So if there are groups of people who are already struggling because of other issues, then potentially this would be a good idea to vaccinate them as well. So I mentioned that we would get back to talking about herd immunity. So herd immunity is from the farm. So you don't need to vaccinate all cows, just most. And that's something that farmers have always known. But herd immunity is achieved when a large portion of a community becomes immune to a disease, making the spread of the disease from person to person unlikely. And as a result of all of this, the whole community becomes protected, not just those who are immune. Vaccines and natural infection occur in a significant number of people before herd immunity can be reached. It's also important to note that as we're looking at these innovations like vaccines coming out, that there's going to be potentially some pushback. And some of the issues will be around reactions. As I mentioned before, people may have reactions such as muscle aches and fever and headaches and joint pain, things like that. We are already aware from clinical trials that serious reactions are rare, but they do occur. And so again, people may have allergic reactions, and those are things to be concerned about and are serious events and need to be addressed. But one of the things I think is really important to recognize is that people naturally have many health challenges. So I used to work in the emergency room, and I can tell you that stuff happens every day, right? We have people come in, there are car accidents, there are people falling off of balconies, there are workplace injuries. But some of the things that are important when we're giving out vaccines to consider is that things are going to happen like heart attacks, right? So someone in America has a heart attack every 40 seconds. So someone is going to have a vaccine and then subsequently in a short time after that have a heart attack. Someone is going to have a vaccine and then they're going to have a stroke. Well, every 4 minutes in the US, someone dies of a stroke. So the fact that someone's going to have a stroke is unfortunate, but it will happen. And about 8 people in 1,000 have regular seizures. So someone's going to have a vaccine and then someone's going to have a seizure. And I'm not saying that we wouldn't be concerned about that. Of course we would. But the two may or may not be related, and we just need to keep an open mind about that. So what epidemiologists will be looking for is an excess in death and disability, not what is expected. So we already know what we would expect to see. what we're going to be looking for is, after a vaccine, is there more than of these things that we'd be concerned about than we would see if there wasn't a vaccine. So that's just something to be considerate of. And a lot of these issues and health problems and deaths occur seasonally. So one of the things we know is that people have more cardiac related deaths, for example, in the wintertime than they do in the summertime. So so we'll look at all of that and obviously be keeping track to see that if there is an excess number of deaths and disability, that we address it. All right, and there's also some lingering questions about vaccines. So will vaccinated people be prevented from transmitting the coronavirus? Actually, to be honest, we don't know. So if you're vaccinated, how likely are you, and you have coronavirus then, to transmit? We don't know. How long will vaccine or infection protection last? We don't know. We know that when people have a naturally occurring infection, that we can see antibodies for 3 to 4 months afterwards. So that's interesting, but it doesn't really tell us a lot about whether or not they are immune during that time, or whether they're immune for much longer, or whether they have partial immunity. So we don't know. We also don't know how long it will take to vaccinate the whole population, or how long it will take to reach herd immunity, right? We don't know that yet. And of course, who should get the vaccine first? There's still lots of debate about that. Should it be healthcare workers? Should it be elderly people? Should it be people who have other disparities for social justice reasons? Who should be getting the vaccine first? Now let's move on to testing. This is one of my favorite subjects, and there's lots of interesting innovations that have taken place in testing. So before we get too far into it, I want to tell you that there are two very different kinds of testing when it comes to COVID-19. We can do antibody blood tests. So when we talk about antibody testing or serology testing, this is to help people understand if they've had a prior infection or exposure to COVID-19. This means that you've had, at some point in your experience, in the few months before, could have been yesterday, could have been 5 days ago, or it could have been 5 months ago, but at some point that you had an exposure to the virus, and you may have been asymptomatic. But if you get a serology test that's positive for COVID-19, a blood test, that means you have antibodies. And for most accurate results, actually, an antibody test should be taken about 3 to 4 weeks after either you've had symptoms or you had some kind of exposure that you want to pin down, to say, yeah, that I was at that party and those people got infected, and yeah, now I also have antibodies. And they can be detected for a number of months, as we mentioned, post-exposure as well. But having antibodies doesn't infer immunity. So it's absolutely something interesting that we'll be looking at. We'll be looking at antibody titers as well when we have vaccines, and we'll be interested in this. But at this point, antibody blood tests are not the kind of testing that you probably have been thinking about, or maybe have even had. The other kind of test is what we're looking for is actually in viral shedding. So now we're not looking for whether or not you've been exposed and you have antibodies in a blood test. For these tests, we're actually looking at, are you currently infectious? Because if you have virus that you are shedding at this point in time, that you are spewing, that is coming off of you, then we want to know that. So this is the most common type of COVID testing. And most of the time we do this through a nasopharyngeal swab that takes this long Q-tip-like swab and puts it right up into your nasopharyngeal area. There's also nose ones. There's some nasal swabs. There's also throat swabs. And there's some swish and spit, right? So there's different ways of doing it now that you can get. And this shedding virus is going to be very important for lots of reasons. Because if we understand whether or not someone is shedding virus, not whether they have antibodies and were exposed months ago, but whether they currently are shedding the virus, that's going to help us so much with travel. It's going to help us with who should be at work. It's going to help us if you find out that you were exposed to somebody and you think about the timing and you work it out and you're not shedding virus. That's going to be very important for you to protect your family and all the people around you. And there's some really exciting innovations that are coming out in testing. And one of the examples is this lovely, lovely little Spartan Cube. And the Spartan Cube is a DNA analyzer. It's about the size of a coffee cup. And you take samples from your nose and insert them into this little single-use DNA test cartridge. And then you put it inside that little box, which is the analyzer. Then the cartridge extracts DNA and makes millions of DNA copies. So an optical system that's inside that little analyzer then detects the increased fluorescence and algorithms and automatically generates a test result and then Bluetooths it to your phone. So what's going to be happening fairly shortly is you're basically going to have a little lab in your home or at your church or at your workplace or at a concert that's going to be able to help us all to know who is currently shedding the virus. Doesn't mean you do or do not have an infection. It doesn't mean whether you have antibodies, but it would tell us if you're currently shedding SARS-CoV-2. So if all these people are being tested, which we are seeing lots of people being tested now, people staying home, people doing why is the incidence of COVID-19 still rising? One of the important things I'd suggest is that it's a matter of timing. The incubation period for COVID-19 is between 5 and 7 days. Therefore, if you have an exposure that causes an infection on a Monday, you may not test positive until Saturday or later. So even if you tested in the meantime, you probably wouldn't show. You wouldn't test positive likely. So let's think of the sequence of events. So imagine on Monday you visit your friend Sal, and Sal has COVID-19 and is infectious but is not yet showing symptoms. So you have a nice little visit, you hang out, and unfortunately some of that virus gets into your body and then it injects its RNA into some of your cells and starts to replicate. On Tuesday you attend work and although the virus has infected your cells, you're not yet infectious and you feel good. And then on Wednesday, you feel great actually because you've got this great party that you're going to be going to and your friend's house and at his home and you're like, yeah, this is going to be great. What you don't know is you're starting to become infectious. By Thursday, you start to feel unwell, but not so much that you need to stay home from work or anything like that. In fact, after work, you go out and you do some shopping and then you think, well, I got this bit of a scratchy throat and I'm not feeling that great. I'm going to go get some flu medicine. So you also go to the pharmacy. Unfortunately, on Friday, your throat's sore and your eyes are puffy and you might not even go into work that day. You're thinking, I probably have a cold. And thankfully, your elderly relative hears about this and comes by with some soup and encourages you to, be well hydrated and hangs out with you and keeps you company while you're home from work. Uh-oh, that's probably a bad idea, right? Because if you look at the little scale underneath, it's showing you that how sick you feel is you're not so bad until maybe a little bit worse on Thursday. Friday you start to feel worse, and then by the weekend you're really, really sick. But how contagious you are goes up much sooner. And that's the problem with COVID. That's the problem, is that you are contagious before you feel sick. And so even if you're the kind of responsible person who's going to stay home or is able to stay home and avoid other people, you're already contagious by the time you even know that you have it oftentimes. And as we said before, about 17% of people don't even know that they have it because they're asymptomatic. So now let's move on to public health controls. So much of what we do to stay safer is what we've already been doing. So what do we know about these things? What do we know about physical distancing and avoiding crowds, about isolating, about using PPE and maintaining hygiene, about cleaning and improving ventilation and filtration? We know quite a bit, but maybe there's some things that we can remember. So it's really important as we review some of the things that we've maybe already been dealing with since the beginning of the epidemic, to consider them as now very evidence-based, because we've actually been gathering information about the epidemic as we've been moving forward. And even though the epidemic is less than 1 year old, we're still able to have reflected on and considered and collected data on what we now know to be good practice and best practice during the time of the pandemic. So let's think about this. We don't want to be a spreader, so we're going to distance ourselves wherever possible. You're going to stay home if you're sick, and you're going to get tested if you have symptoms. And when you're in close proximity to someone, you're going to use PPE, and that might mean wearing a mask. You're going to limit the time that you are there with that other person, and of course you're going to wash your hands properly as well. So how do we keep distance from others, and why do we do so? Well, SARS-CoV-2 is a droplet-borne disease, mostly. There are other ways that it spreads, but most of the time it's spreading by droplets. And that means that whenever we're within a 2 meter or 6 feet distance from another person, there's the potential that they're going to be shedding or spreading droplets, and we're going to be breathing them in. So you think about droplets, you think, well, how many are there? I mean, they're droplets, yes. We've had someone who's sort of been moistly speaking and get some of the sputum on you, and you think, oh, that's terrible, someone just spat on me. But actually, the droplets are common. Sneezing contains up to 40,000 droplets, and coughing contains about 3,000 droplets. So if you consider that if you're in a close distance to somebody and they're speaking, there's going to be some droplets, but if they're coughing or sneezing, you're going to actually potentially be in a rain of droplets. And the number of droplets, of course, varies by person. And the things that influence that are usually light, so UV radiation, the airflow in the room, and the environmental humidity. So you can imagine that being outdoors is much safer than being indoors. Droplets can travel far. So they can travel as far as 2 meters, and that's where we get that 2 meters distance, or 6 feet. We actually want people to be outside of the distance that droplets can travel. Soon after leaving the human body, though, droplets begin to evaporate and they lose mass. So the largest droplets completely evaporate before hitting about 2 meters away. But smaller droplets can travel. And if you're sneezing, then those droplets can travel up to 6 meters. If you're coughing, about 2 meters. And just normal breathing would be likely smaller droplets would evaporate within a meter. So this is what it might look like. So imagine I'm the person on the right and I'm walking past somebody on the left, and the person on the left has COVID-19. So as we're coming towards each other, at a distance of 6 meters, if he sneezes, I actually can breathe in some of those virus. At this point, if he coughs, I won't be able to, but as you can see, by the time I hit 2 meters, I potentially could, and then just his normal breathing, I would have to get about within 1 meter distance. When a person breathes in, they inhale air from a pocket of air that's about 15 centimeters tall. So if you took a ruler and broke it in half, that's about 15 centimeters. So air is flowing from the lower part of the human body and is drawn up into the mouth of the person that's breathing in. And about 2/3 of the air that I breathe in is coming from below my mouth. And keep in mind that hot air rises. So the person that's exhaling is exhaling hotter air than the ambient temperature, likely. And the person breathing in, therefore, is breathing up that air that's coming at them. So let's look at these two people. We have person A and person B. Person A has a respiratory infection and is breathing out, releasing a cloud of droplets of various sizes. Well, lots of things that we'd have to ask about transmissibility before we thought whether this was a problem. Like, how fast is the cloud being released? Are they breathing? Are they talking, singing, laughing? Are they coughing or sneezing? And how quickly will the droplets evaporate? What's the humidity and heat in the room? And then we also want to look at person B, who is not infected with a respiratory virus. As she's breathing in, how far away is she standing from person A? And for how long are they talking? And what's the airflow in the room? Is there good ventilation? Is there air conditioning? Are there windows open and doors? And is she breathing through her nose or her mouth? And what is the status of the little hairs, the cilia, that are all throughout the respiratory system that aim to keep us safe from viruses? Let's look at this picture and just do a little review. So we've got person A and we've got person B, and person A has an infection. So that person is breathing out, and the two people are within 1 meter of each other. Person B is breathing in, and remember there's that 15 centimeter, about 2/3 below the mouth, that they're breathing in from. Because person A in the first scenario is wearing a mask, most of the droplets that are coming out of that person are kind of falling around their face. Some of them are being caught in the mask, which is why your mask gets wet, and some of them are falling around the sides. The better the mask fits, the less likely they'll be doing that. But even if the droplets are falling around the sides, they're unlikely to be breathed in by person B. But in the second scenario, those two people are within a meter of each other, and there is no mask between either of them. And person A has the virus, so as they're breathing out, person B will likely be breathing in a significant amount of virus. Now, that doesn't mean that that person is going to get infected with COVID-19. However, it certainly increases the chances because person A, who has the virus, is not wearing a mask. Now let's look at objects. I said that most of the time SARS-CoV-2 is transmitted by droplets, and that's true. One person breathes out and one person breathes in. But another thing that happens is that somebody who has the virus is also shedding those viruses or spewing those viruses on objects. So in this case, person A, who has the virus, could be shedding the droplets on the cup, on the computer, on the handbag, on the desk itself, and person B comes along and maybe they're not able to breathe anything in, but they're going to touch those things, and maybe then they rub their eye or eat something or drink something, or maybe the droplets do just fall into their eyes. So those are some concerns, but wearing the mask certainly prevents many of those viruses from getting on those objects. So here we have another scenario where it's possible that the cloud of mucus that the person, who in this case is Taylor, is breathing out and Taylor is infected with the virus, could potentially drift on the air for about 8 minutes. If this is a stagnant kind of a room, there's not good ventilation, there's no windows open or doors, and we're in a small room together, could even be an elevator. Well, what's going to happen? So the average person speaking generates airborne droplets that can remain suspended for tens of minutes and are capable of transmitting diseases in confined spaces. So in this case, we've got two people, Jordan wearing a mask and Kelly not. Who would you rather be? Would you rather be, in this case, Jordan or Kelly? If there's a cloud of gas going around, would you rather be breathing through a mask or not? Masks aren't perfect. They don't prevent 100% of disease. But surely to goodness, in this case, you'd rather be Jordan than Kelly. And what if Taylor was wearing a mask? Wouldn't that be better? And wouldn't that protect both Jordan and Kelly? Maybe Kelly can't wear a mask for whatever reason. So it would be important that Taylor was wearing a mask to protect both of those other people. We want to, of course, be covering our coughs and our sneezes. We call that cough and sneeze etiquette. We want to make sure that we're not around people who are coughing and sneezing, first of all. But if someone does cough, make sure that they cough into their inner elbow, as shown in the picture here, and cough and sneeze with a tissue. And then after you cough or sneeze into a tissue, discard that tissue and then wash your hands. And make sure that people with coughs, for whatever reason, are wearing masks. So I've been around people that have said, it's fine, I have allergies. People with allergies shouldn't be coughing in the time of a pandemic around other people without wearing a mask. So masks are still necessary. Wash your hands frequently with soap and warm water for at least 40 to 60 seconds. And you can even sing in your mind the birthday song if you want to. We also want to use proper alcohol-based hand cleaning products as well. And the reason for this is, remember we mentioned that there could be somebody who is spewing virus, who's touching, in the case that there was a computer and there's a purse and there's a cup, they're touching things, or even they're just breathing on things. We want to make sure that when you touch things, you wash your hands properly or sanitize them so that we don't end up having infections transmitted through contact. We also want to make sure that we clean things. And we're going to clean things with soap and water, and then let them dry, and then spray something on them like Lysol or whatever to sanitize if there's any chance that there could have been some sort of exposure to a person who has COVID or somebody who has sneezed or coughed on something. And of course, you're going to wear gloves whenever there's any chance you're going to come into contact with body substances. So if someone has had a bleeding nose or has coughed on something, make sure that you're wearing gloves when you clean up after them. Let's now look at ventilation and filtration. So ventilation improvements can be made and really should be seriously considered in any work environment or any living environment. So what we want to do really importantly is increase outdoor air ventilation. Whenever we can, when weather conditions allow, make sure that there's fresh air coming in by opening windows and doors. Florence Nightingale had this thing where she would actually twice a day open all the windows in the hospital and made sure that people had fresh air every single day. You can use fans to increase the effectiveness of open windows. You can even put a fan in a window. And make sure if there is a space in your workplace or in your home or somewhere else where ventilation can't be increased, then make sure people are not there for very long. So decrease any occupancy in areas where outdoor ventilation can't be increased. And make sure you look at your HVAC. Turn off any controls that reduce air supply based on occupancy and temperature. So lots of wonderful people have switched their HVACs to help the environment by making them turn off when there's not people around or turn off when the weather is mild. But we actually want lots of air exchanges, and I know it drains power, but it's really important to have that for the pandemic. We also want to open any outdoor air dampers, so make sure that you have a look at your HVAC system and make sure that the air is not recycling. And if you have a restroom with exhaust fans, make sure that they're operating at full capacity, because toilets unfortunately sneeze, and people who have COVID-19 may be shedding virus in their urine and feces, and then you flush the toilet and that goes everywhere. We want to get that air out of that room. And then even in places like kitchens and cooking areas where there are ventilation and exhaust systems, make sure that they're running and running even when there aren't people cooking, but people are just there. You also might consider some kind of portable high efficiency particulate air or HEPA fan or filtration system to enhance air cleaning, and consider using ultraviolet germicidal irrigation as a supplement to help inactivate SARS-CoV-2 as well. So are any one of these public health interventions enough? I don't think so. I actually think we need to do all of them. You might say, well, I'm going to do this, but I'm not going to do that. Well, consider this. If we think of public health activity as a block of Swiss cheese which has been cut in several slices and randomly moved about, if we want to stop transmission from moving through that, some say air from moving through that cheese, we can't stop it with one individual slice. So in this case, look at physical distancing. Physical distancing decreases the risk of transmission by 10.2%. That's not that much. But eye protection also decreases transmission by about 10.6%, and wearing a mask by a further 14.3%. And all those other things that we know are effective, but we don't have studies for yet, like hygiene and cleaning and sanitizing and other things that we know to do right, also reduce the risk of infection. So we can say that any one intervention is not that helpful, but as we layer them and put more and more interventions together, we're going to soon have a fairly opaque block of cheese, and we're not going to have holes in that and encourage transmission. So we don't want to do that. We want to make sure that we do all the things we know to put them together to build a stronger public health prevention activity. And there are so many other innovations on the horizon. I am so hopeful about the future and about what's going to be happening with COVID-19. Look, we're going to have UVC lighting, we're going to have 3D printed swabs, better use of AI for patient data, we're going to have better low-cost and environmentally friendly gentle ventilation. We're going to have great treatments. Things like iodine are being used and monoclonal antibodies. So I feel very, very hopeful about the future. And I don't want anyone to kind of lose hope at this point, because good things are happening. The vaccine is here. We just need to kind of roll it out and tighten it up and make sure that we're doing testing and that we're keeping on top of our environmental controls. And things are going to be much, much better for 2021. So thank you for listening to this module. Those of you who are going to be doing the quiz, I invite you to do that now. And I'm very thankful that you've joined us, and we really hope that you are working with us to save lives and to make our environment safer.